As part of a research project, the masses of a random sample of 1,000 pebbles from a certain beach were recorded. The results are summarized in this table, this grouped frequency table. We're asked to calculate estimates of the mean and standard deviation of these masses. So the first thing to do is let's get the midpoint of each group, because some of the masses are going to be at the lower end, some at the higher end. We're averaging them out. We're saying they're all going to actually be in the middle, um, because then it cancels out the ones larger and the ones lower. So I'm just going to write these down. And then we need to, yeah, that is enough to now calculate the mean and standard deviation. Now you could do it the long way and use the formulae, but this is only a 2 mark question. It is expected that you use your calculator, so I'm just going to show that method. Okay, statistics, one variable, and then you've got, you should get a frequency table up. If if it doesn't say frequency, then you need to go to your setup and then statistics and make sure your frequency is turned on. And go to option, one variable calculation, and we can just read it off. We've got 201.225, which this is an estimate, remember, so we can't do any better than three significant figures, but we'll write down three significant figures. And I'll write grams. Yeah, it's not too important. I should probably say approximately, actually, because that's what they are. And the standard deviation, here we go, sigma x 60.738, or 60.7 grams. Now, the masses of a random sample of 1,000 pebbles on a different beach are also found, and it's proposed that the distribution of these masses should be modeled by this random variable, a normal distribution. Note that the variance is 3,600. The standard deviation would be the square root of that, which ends up being 60. And we're asked to use the model to find this probability. Again, it's just something we can put in our calculator. This time it's to distribution, and it's going to be normal CD. That allows you to do a range of values. Lower is 150, upper 210, standard deviation 60, and mean of 200. Gives 0.3638. Just a reminder of what is actually happening. We have a normal distribution, center at 200. We've got 150 here, 210 here, and our calculator is doing an integral to find this area. There is actually an equation that you can write down for the normal distribution. It's in fact an e to the minus x squared sort of one, but this goes beyond the syllabus. You don't need to actually know about that, but it is of interest, and you might want to look into it. But yeah, the calculator is doing a numerical integration to work out that probability. Then we're asked to use the model to determine x1 such that this is true. Okay, I think a graph is definitely going to help now. So we've got another normal, well, the same normal distribution, and I'm going from 160 to x1, and it's 0.6, so it's going to be the other side for 200. Okay, we want to work out x1. Now, what we can do, so we actually know what this is, But what I'm first of all going to do is work out the probability that x is less than 160, because then I can work out the entire bit to the left of x1, and then we can use inverse normal. So just make your lower a large negative number. I just tend to write lots of nines, but you might write 10 to the 6 or something. 160, and this gives 0.25249. Now, the final answer is meant to be correct to 5 significant figures. So you know what? I'm going to write another 2, 2, 5. Okay, because that means that the probability that x is less than x1 is going to be the sum of the 0.6 and the 0.2524, etc. So I'm going to get 0.8524925. And that is set up for the inverse normal. That is precisely what the inverse normal does. It's always to the left. When you do the inverse, it will tell you what that limit is from minus infinity to x1. So do you know what? I'm just going to actually store that. And then I'm going to add the 0.6. So I've got the exact figure. Okay, but it would be enough with the figures I've used. Then I'm going to store it again as A. Back to distribution. Inverse normal this time. Our area is A. It's 0.85. Okay, I'm going to have to put the standard deviation back in because I lost it when I changed mode. And we get 262.831, which becomes 262.83. It was found that the smallest and largest masses of the pebbles in the second sample were 112 and 288. Use results to show that the model may not be appropriate. So this is where we need to use some properties of the normal distribution. And I'll talk about the mark scheme in a minute and what they're looking for. I'll tell you what I did. So we know for any normal distribution that approximately all the data, I think it's actually 99.7%, is contained within 3 standard deviations of the mean. So that means the model predicts that the smallest weight, or mass, I should say, is equal to 200, that was the mean, minus 3 times 60. So is 20 grams. And this is like significantly less. That's a way to write significantly less. Maybe that's a bit overkill. It's not like, but this is much less than 120 grams. And then the greatest mass prediction is going to be 200 plus 3 times 60, which is 180 plus 200, so 380. So this is much more than 288. And therefore, I mean, that's enough to say, therefore, the model may not be appropriate. The mark scheme does a slightly different thing. They just say that 112 and 288 are within 2 standard deviations of the mean. So actually 95% of your data is within 2 standard deviations of the mean. So they're kind of using the outer limits as the 2 standard deviations, but because it's within, it's not, it's not good enough. Basically, that's why the model isn't going to be valid. But they do talk about the 3 standard deviations over here. So I actually think that's a better answer, but there we go. We're then asked to suggest a different value of the parameter of the model in the light of these results. And again, different things are allowed. But I said, okay, I'm going from 112 to 288. I need that to be 6 standard deviations because I'm trying to have like all of my data within this amount. So 6, that's meant to be a sigma. Let me give it another go. A bit better. Okay, that is going to be 288 minus 112. By the way, you can see that these are each 88s to the side of 200. So we do seemingly have like symmetry going on. So that ends up being 176. And then sigma is 29.3 or about 29. I mean, it's a model. I guess 29.3 is like, let's be as accurate as we can to make it 100%. So that is definitely an allowed answer, and it follows on from what I did in part D. The mark scheme follows on from what they did in their part D, and they say to reduce the standard deviation. That is a key thing, as long as you say that. And then they actually set it equal. They do 4 standard deviations essentially, because they do the 288 minus the mean, but it's equivalent to setting 176 equal to 4 standard deviations. So they're trying to get like most of the data. Um, so as long as you can show your justification, they get 44, but the mark scheme talks about 29.3. All of these are allowed. It's just essentially making sure in this question, like it's testing us on our understanding that the data is within these realms. It's not an exact science. I think that's the main thing. So that's why like 2 standard deviations, 3 standard deviations, both okay, both accepted. I am still shouting for 3 standard deviations, but that's my opinion on it. Anyway, well done on this question.